Okay. Now, if you take an individual reading, in this case here, the precision was 0.01, and you had one reading, say 5.10, your margin of error would be, millimeters by the way, would be the half of the smallest that you can get. So it would be 5.10 plus or minus 0.005 would be what you would say is your uncertainty in the reading. It's the smallest, it's half the smallest division that you can measure. Okay, but because you've got 5 readings here, you have to use a different technique. You have recognized you've measured the same thing 5 times, but you're getting variation here. So what you do is you work out the mean, and if you do the mean of those results, I can think it's going to be 5.12. So 5.12 will be the mean. And then in order to work out the uncertainty in your measurements, you look at the biggest number, 5.14, and the smallest number, 5.10, and that gives you your range. Your range is 0.04. And if you divide that by 2, that will give you your error, your margin of error, 0.02. So the final answer you give is 5.12 plus or minus 0.02 millimeters. And in this case, that is the answer there. Right, in this case here, okay, so this is a stack of 50 pages. Okay, you've got 50 pages here. And your accuracy in measuring this page is plus or minus 0.1 millimeters. The good thing about measuring, say, 50 pages is that you know that when you measure the thickness, you've got 50 pages, so you divide it by 50. It has the effect of dividing the absolute error by 50 as well. So this error of plus or minus 0.1 millimeters is going to become an error of 0.01, divide it by 50, or plus or minus I should say, and that will give you, which is 0.002. So 6.5 millimeters divided by 50 gives me the answer 0.13 plus or minus 0.002 millimeters, and the answer to that one is that one there. Okay, good. Right, what do we mean by an error? Right, the key words here is an error is a deviation. The key word is a deviation of measurement, a deviation of a measurement from its true value. A deviation of the measurement from the true value. These are the magic words. Deviation of measurement from its true value. Okay, that's how it's defined. You must remember that. Okay, you have to learn it. What's the difference between a random error and a systematic error? Right, in a random error, what we're really looking at there is the errors are unpredictable. Okay, they are unpredictable. And the other thing is to talk about the fact that it is a variation of measurement, a variation of measurement that is unpredictable. Okay, the systematic error is where the measurement is consistently, that's the key word, where the variation is consistently too high, or the deviation from the true value is consistently too high or too low. Too high or too low from the true value, or too low. Okay, explain why taking an average of several readings will reduce random error, but will not reduce systematic error. Okay, well, what you need to say here is that the random error has an equal chance of being positive or negative. So when a mean is taken, they tend to cancel out. So yeah, it tends to be plus or minus. So over a period of time, if you take like 100 readings, the pluses and minuses almost nearly even out, or may even out. So they cancel each other out. In a systematic error, though, you are consistently too high. So your average will be consistently too high. Okay. D. How would a graph show evidence of systematic error? Okay, brilliant. Okay, so let's imagine you were plotting something like force against the acceleration of a trolley. Okay, so this is investigating famously Newton's second law. When you plot the graph, you might get a lovely line like this. Okay, and it should really go through the origin. The fact it's not is showing that something bizarre was happening. It was suggesting that when there was zero force, there was an acceleration. So that could be an indication that the trolley was on a slope. In this case, when it was zero, you had an acceleration already. So it suggests the trolley was already on a slope rolling down the hill, potentially. So it's the way you know that you've got a systematic error is when you plot a line, a graph or a line graph, and your intercept on the y-axis is either too high or too low. Okay, or too low. If it goes to zero, you know you haven't got a systematic error. How might a graph reveal a random error? Well, again, the same sort of concept. If you have plots all over the place, but there's roughly a pattern like that, then you know that, well, there's a fair degree of variation there. There's quite a lot of random error there. But if the plots are all close to the line of best fit, like here, for example, you know that your measurement has been fairly accurate. It's been very close to the true value, with the exception of the systematic error. So you've been consistently too high, but you've not been too far away from what it should have been, with the exception of the consistently too high. So this has got a large random error, very little random error, but it has got a systematic error. Okay, I hope you found that of use.